Hello and welcome to this introductory presentation related to heat transfer through walls. To calculate the heat transfer Q through the wall, we will make use of the formula Q is equal to KAT divided by X. We'll define the formula later. This presentation essentially provides the underpinning knowledge for the following presentation related to heat transfer through composite walls. Presentation overview. We commence with an introduction stating the factors that affect heat transfer and also stating and defining the formula Q is equal to KAT divided by X. We'll define the variables on the next slide. Then we have example 1, where essentially we use the above formula to calculate the heat transfer Q through a glass window. Then we have exercise 1. Here we calculate the heat transfer per unit area. In this presentation, I use lowercase q to denote heat transfer per unit area, and the formula simplifies to Q is equal to KT divided by X. In other words, we've omitted the A term from the equation. So then we have a series of questions for you to attempt that are primarily based on the example and the exercise. So question 1A and question 2A, based around example 1, they calculate the heat transfer capital Q. Question 3A does require some transposition to rearrange the equation Q is equal to KAT upon X for variable X, which is actually the wall thickness. Question 4A also requires some transposition to calculate the outside wall temperature, often labelled as T2 within these calculations. Finally, question 5A is based on exercise 1A, calculating the heat transfer per unit area, denoted as lowercase q here. And here are the approximate start times related to the various sections contained within the presentation to hopefully aid your ease of access through the presentation, but please note the times are rounded to the nearest minute. Transmission of heat energy. Let's consider the factors that affect conduction through a flat plate or a wall. Firstly, the type of material used in the construction. Secondly, the temperature difference of the faces through which the heat energy passes. 3. The time taken for the heat transfer to occur. 4. The cross-sectional area through which the heat transfer takes place. And 5. The length or the width of the material used. Transmission of heat energy continued. So the rate of heat transfer, denoted by the symbol capital Q, has the unit of the joule per second, that's the energy transferred per unit time, but often this derived unit is more commonly known as the watt. So Q has the unit of the joule per second or the watt. The formula for Q is stated in the bolded box here, and it's Q is equal to K multiplied by A multiplied by T. And that's all divided by X. On a diagram, capital Q is shown here, and that's the rate of heat transfer through the wall. Considering our nomenclature, symbol K relates to the thermal conductivity coefficient for the particular material. That's often specified in terms of the unit of the watt per meter per Kelvin, or of course the watt per meter per degree C. I'm using the negative index notation here, but do note that the unit of K can be specified in other formats, as shown here, the watt per meter per Kelvin, or in this form, watt per meter per Kelvin, or this form, watt per meter per Kelvin. And we'll use these various forms throughout the presentation to aid your familiarity with them. Symbol capital A relates to the cross-sectional area of the plate or the wall, and that must be in meters squared. And capital T relates to the temperature difference across the wall, where T1 is generally the inside surface and T2 the outside surface. And from our previous presentations, we know that this temperature difference can be specified in either Kelvin, K, or in Celsius degrees C. 1 K rise in temperature is equivalent to 1 degree C rise in temperature. Finally, symbol X, depending on the context of the question, can relate to the length or the width or the thickness of the wall or plate, and that must be in meters. Symbol X shown here on our diagram. So that's the formula we'll predominantly be using throughout the presentation. There is a slight variation in the formula when we calculate the rate of heat transfer per unit area, but I'll show you that simplified formula when we're required to use it. Transmission of heat energy continued. So here's example 1a. A glass window measures 1.3 meters by 1 meter and is 4 millimeters thick. If the temperature of the inside surface, labelled as T1 here, is 10 degrees C, and the temperature of the outside surface, labelled T2 here, is 5.5 degrees C, we've got to calculate the rate of heat transferred, that's capital Q in this case, through the window. We can assume that the coefficient of thermal conductivity for the glass to be 0.95 watts per meter per degree C. So let's extract the information from the question. We know the dimension of the window, it's 1.3 meters by 1 meter, so we can calculate the area of the window A, it's 1.3 meters squared. The window thickness, X, is given as 4 millimeters in the question. We will convert that straight away into meters, so 0.004 meters. And the temperature difference, capital T, is T1 minus T2. The inside surface temperature is 10 degrees C. The outside surface is 5.5 degrees C. So our temperature difference is 4.5 degrees C. We're given the thermal conductivity coefficient K in the question, it's 0.95 watts per meter per degree C. So to calculate the rate of heat transfer, capital Q, Q is simply K multiplied by A multiplied by T, and that's all divided by X. Inserting the values into the formula, the rate of heat transfer is 1.39 kilowatts to 2 decimal places. So that's a typical example of how to use the given equation to solve for the heat transfer through, in this case, through a glass window. Here's exercise 1a for you to attempt. The inner surface of a 250mm thick plain brick wall is at a temperature of 40 degrees C, and the outer surface of the wall is at 20 degrees C. We're asked to determine the rate of heat transfer per meter squared, that will be symbol lowercase q here, of the surface wall area. We're given the value for the thermal conductivity coefficient K for the brick, it's 520 milliwatts per meter per Kelvin. Note the formula for calculating the rate of heat transfer per unit area, per meter squared in this case, is given in the bolded box here. It's lowercase q this time, is equal to K multiplied by T and divided by X. So note the area term is removed from the equation when calculating rate of heat transfer per unit area. Unit of lowercase q will actually be the watt per meter squared. Answer is shown in the bracket. I would encourage you to stop the presentation and attempt exercise 1a, but the solution is shown on the following slide. So exercise 1a, here's the solution. As always, carefully extract the information from the question. Notice the thermal conductivity coefficient K is actually stated in terms of milliwatts. So in the question it's 520 milliwatts per meter per K. I've actually written that here as 520 milliwatts per meter per degree C, which of course is correct. On the next line I've accounted for the milli prefix. So I've actually stated the K value as 0.52 watts per meter per degree C. The wall thickness X in the question is stated in terms of millimeters, so I convert that straight away into meters. And the inside temperature T1 is stated as 40 degrees C, and the outside temperature T2 is stated as 20 degrees C. So I can evaluate from that the change in temperature, which is 20 degrees C. So now I'm being asked to calculate the rate of heat transfer per meter squared. So within this presentation, I'm using lowercase q to denote this quantity. So the formula is KT divided by X. Inserting the values, the rate of heat transfer per unit area In this case is 41.6 watts per metre squared. So here are some tutorial questions related to heat transfer through walls. Essentially, I'm going to let you review these questions at your own pace. They're predominantly based on the example and the exercise we've just reviewed, but I will show the full work solutions to all questions. So in question 1a, we've got to calculate the rate of heat loss through a block wall. We're given the value of K in the question. We're given the dimensions of the wall and its thickness. There are two parts to the question. The first part wants us to calculate the rate of heat loss if the outer surface is 12 degrees C and the inner surface of the wall is 20 degrees C. And part 2, we've got to calculate the rate of heat loss if the outer surface of the wall is negative 5 degrees C, often referred to actually as minus 5 degrees C in general parlance, and the inner surface temperature is 21 degrees C. Answers are shown in the bracket here to 1 decimal place. So now I'd encourage you to start the presentation and attempt question 1a, calculating the rate of heat loss, Q, using the appropriate formula here, for the two instances stated in the question. The full work solutions are shown on the following slides. So here's question 1a, this is part 1, solution. I'm going to let you review the solution at your own pace. For part 1, the value of Q is 2,118 watts or 2.8 kilowatts to 1 decimal place. And here's question 1a, part 2. Again, I'm going to let you review the solution at your own pace. Just be careful when calculating the temperature difference, labelled T2 here. The inner surface is at 21 degrees C, but the outer surface is actually at negative 5 degrees C. So in our calculation we have 21 minus the negative 5. So that becomes 21 plus 5. So the change in temperature is 26 degrees C. Just be careful with your calculation for the temperature difference. For part 2 of question 1a, the heat transfer Q2 is 9,152 watts or 9.2 kilowatts to 1 decimal place. Question 2a, we've got to calculate the rate of heat loss through a piece of insulation board. We're given the dimensions of the board and the thickness. We're given the temperature of one surface is 300 degrees C and of the other surface 20 degrees C. The value of K is given in the question. Again, we've got to calculate the value of capital Q in our equation. Answer is stated in the bracket here. Again, I would encourage you to attempt the question before I show you the solution on the following slide. So question 2a, here's the full solution. Just be careful in the question. The dimensions are stated in different units. We have 2 meters by 750 millimeters, which of course is 0.75 meters. So calculate my area, always in terms of meters squared. And also notice that the thickness is stated as 1 centimeter. So again, be careful, that's 0.01 meters. The value of heat transfer Q in this case is 840 watts or 0.84 kilowatts. So here are 3 further questions. In question 3a, we have to actually determine the minimum thickness required, symbol X, given the various parameters here. So in this case, the actual value of the heat loss, capital Q, is stated in the question. It's 0.35 kilowatts. So question 3a does require some transposition to find the value of X. Question 4a, this time we have to determine the final temperature, labelled T2 here, of the outside of an oven, given the inside temperature, labelled T1. Again, we're given the heat transfer in this particular case. We have the wall thickness given to us. And notice they've actually stated the area this time. We do not need to calculate the area from the dimensions. The area is actually given. K is also given in the question. And finally, question 5a. This is very much like the exercise 1a because we have to determine the rate of heat transfer through the wall, but per metre squared. So that's lowercase q in this presentation. So again, I would encourage you to stop the presentation and attempt these questions. The answer for question 3a, the thickness is shown here. The answer for question 4a, the outside temperature or the final temperature shown here. And for question 5a, the answer is shown here. Again, just for convenience, here's the formula we'll be using to solve questions 3a and 4a. Note that question 5a is essentially based on exercise 1a solution. So I now encourage you to stop the presentation and attempt question 3a to 5a. The full work solutions will be shown on the following slides. Here's question 3a, solution. We're required to calculate the minimum thickness, labelled as x in our diagram. So first, as always, extract the information from the question. So to calculate the minimum wall thickness, x, we need to transpose our formula. That Q is equal to Ka T divided by x. We need to transpose it for x. So to do that, we simply multiply both sides by x and divide both sides by Q. So our formula becomes x is equal to Ka T all divided by Q. Inserting the values, we calculate x to be 0.1375 meters or 13.75 centimeters. Question 4a. This time we're asked to calculate the final temperature, labelled as T2 here. So again, this question will require some transposition of our formula. So firstly, extract the information from the question. Just notice in this question we're actually given the wall area. So no need to calculate it from the dimensions. And just note for reference in question 4a, the conversion required from millimeters squared into meters squared. So here is stated the unity bracket to undertake the calculation. Note the unity bracket is squared here because we're converting from millimeters squared into meters squared. For your reference, there is a separate presentation related to the use of unity brackets. Notice we're given in the question again the heat transfer, 1.1 kilowatts here, 1100 watts. So we're given Q in the question, we're given T1 and X. So now we can calculate the outside temperature, T2. Question 4, solution continued. To define the outside wall temperature, T2, the transposition is slightly more complicated. We know our formula is Q is equal to Ka T divided by X. Note that the T in the equation is actually T1 minus T2. So on the next line here, I've actually replaced capital T with this bracketed term, T1 minus T2. Now I'll undertake my transposition. Firstly, I'm going to multiply both sides by X. Then I'm going to divide both sides by the Ka. And finally, I'm going to add T2 to both sides and subtract the Qx divided by Ka from both sides. So my final formula here is T2 is equal to T1 minus Q multiplied by X. And that's all divided by Ka. So inserting the values from the question, just repeated them here for convenience. This is T1, this is Q, this is X. That's all divided by K multiplied by A. So here's our K value, and here's our A value. It's explicitly given in the question. So final temperature T2 is 22.3 degrees C. So question 4a required slightly more complicated transposition. And finally, here's the solution for question 5. I'm going to let you review this at your own pace. It's essentially the same solution as exercise 1a we reviewed previously. We got to calculate the rate of heat transfer through the wall per unit area. So we're calculating little q in this particular case. Final answer was 121.2 watts per meter squared. Here's the bibliography used to help generate the presentation. As I said at the beginning, this is underpinning knowledge for the following presentation related to heat transfer through composite walls. I hope to see you again for that presentation. Thank you for viewing.